Okay. A hot air balloon is rising from the ground. An onlooker 2,000 feet away is filming the balloon. So let's draw this situation. So I've got some person, 2,000, whoops, I didn't write it right. 2,000 feet away from this hot air balloon that is rising. We're going to have a right triangle again. What is the rate of change of the angle of elevation of the camera? So this onlooker's holding a camera, they're filming it. What is the change of elevation? Elevation is the angle above the horizontal. That's the definition of an angle of elevation. So our angle, theta, is right here where the person is. And we want to know what is the rate of change of the angle of elevation of the camera. So we're trying to find d theta dt. 10 seconds after liftoff, there's our when. T equals 10 seconds. If the altitude of the balloon is S equals 50t squared. Now that's not our equation. Okay, that's a given. Now, what is S? It's the altitude, so S is over here. And we were also given, and I drew it in the diagram, if we make this x, because it's in the x direction, we're given x equals 2,000 feet. Oops, I keep leaving off a 0. Now, our equation is not the Pythagorean theorem because it has to involve theta. Tangent, right? We know the opposite is S. We know the adjacent is 2,000. That's a trig function that goes with tangent. So we have tangent theta equals S over 2,000. All right, so we have our equation. Now we want to take the derivative of it. All right, that there. We're not going to need that because that's x equals 2,000 is already part of our equation, so I'm not going to need it. All right, so we are going to take the derivative with respect to theta this time, because that's what we're looking for is d theta. Nope, sorry. Take the derivative with respect to time of theta, because we're looking for d theta dt. And S is also a function of time, right? It's the altitude of our hot air balloon, and it's given by that equation. All right, what's the derivative of tangent? It is secant squared of theta times d theta dt, because that angle is changing with time as the balloon rises. And the derivative of S over 2,000, well, that's like a 1 over 2,000 times S. And the derivative of S is 1 times ds dt. Okay, so we're solving for d theta dt. secant squared is 1 over cosine squared. So I can multiply both sides of this equation by cosine squared, and we will have d theta dt by itself. Okay, now I'm given s, so I can find ds dt. ds dt is the derivative of this thing right here. So the derivative of 50t squared is 100t. And we know t equals 10 seconds. So if we plug in a 10 there, we're going to get 1,000 seconds. Okay, so let's see what we got going on here. I have d theta dt equals 1 over 2,000 times 1,000. So that's 1,000 over 2,000 times cosine squared theta. So we can write that as 1/2 cosine squared theta. We don't know what cosine squared theta is. We need to go back to our diagram and our when. Okay, so when t equals 10 seconds, what is my s? I'm just plugging into that equation there. 50 times 100 is 5,000. And if I want to get cosine theta, it's opposite over hypotenuse, right? So let's call that the hypotenuse. Or sorry, adjacent over hypotenuse. So my adjacent is 2,000. I need the hypotenuse. How do I find the hypotenuse given the information I have now? Pythagorean theorem. Great. So we're going to get the hypotenuse equals the square root of 2,000 squared plus 5,000 squared. Okay, so our cosine theta is 2,000 over that hypotenuse. And I need to square it to plug it into my formula. So my d theta dt is 1/2 times 2,000 over the square root of all of that squared. And believe it or not, that actually comes out to be a rational number. Okay? So I didn't evaluate it earlier because if I did, I'd have all kinds of rounding error. When in fact, this comes out to be a very nice 2 over 29. So I get that by plugging the entire expression into my calculator. And theta must be measured in radians because we had no degrees anywhere in the problem. And when there's a lack of degrees, that means we are working in radians.